morning to everyone. So today we are going to summarize the syllabus in the third unit, in which there are two parts. The first part is bending stress in beams. Bending stress, or it is also called as flexural stress. Flexural stress. And the second part is shear stress in beams. Shear stress in beams. Simply in beams. I think that we know what is meant by beam, and it depends upon the boundary conditions. They are classified accordingly. And then, so beam is a structural member subject to transverse load. Keep it in mind, transverse load. And then you have to draw the shear bending stress or flexural stress in a beam subjected to a various types of the loading for various types of the beams. So initially, when the bending stress is induced, simply the bending stress is induced due to the bending moment. So practically, the combination of shear force and bending moment. For our calculation purpose, simply neglecting the shear stress, shear force. So it means just we have to find out the bending stress with considering a pure bending portion. So that is the pure bending. What is the pure bending? Pure bending. For example, let us consider a simply supported beam, AB. Right? So two supports are provided at A and B, and a force of magnitude W at a distance small a from the left end, as well as a force of magnitude W at a distance same from the end B, as shown in figure. So after applying or using the boundary equilibrium equations, then the reaction force at end A is W and at end B is also W. If you plot the shear force and bending moment diagrams, so there is the baseline. This is the baseline, right? Very simple. So the shear force is positive up to C, right? And the shear force is negative, so from D to the B. I think that there is no shear force in the portion CD. There is no shear force in the portion CD. It means just consider this portion CD as a pure bending portion. That is the first point. Then if you plot the graph for the bending moment, so no doubt at all, so it will be the bending moment. So then I would like to consider a portion in the CD. I would like to consider a portion in the CD. So this is the portion CD, right? So just it is a beam. It is a beam. So this is the portion CD. It is the pure bending portion. Pure bending. This is the C. This is the D. Pure bending portion. Practically, no one beam is alone with the pure bending. So remember, the shear force is also acting on the beam, which induce the shear stresses also. For the calculation purpose, let us consider a portion of the pure bending in the portion CD, or let us consider a length delta x or dx in the portion CD for the calculation purpose. So then The second one is the simple theory. So what we summarize is just what is meant by pure bending. We know the pure bending. So next one is the simple bending theory. Simple bending theory. Simple bending theory. So just now what we did, we consider a portion dx in the CD. In the CD. So this is a beam, right? A portion dx in the portion CD, subject to a transverse load, right? So this is the position of the beam. So this is the plane AB, this is the plane CD. In between the planes AB, CD, all the layers, that is the upper layer and bottom layer, are parallel to each other. Again, same in size and shape also. So let us consider a line. So at the midpoint of the AB or CD, called as a one layer. So again, so one more layer at a distance. One more layer at a distance. Y from this layer. Say this layer is called as an axis, neutral axis, for example. Why it is called as a neutral axis? So this is the neutral axis. When it is called as a neutral axis. So what is meant by this is the layer F. So if we observe the layer AB as well as the NA and the F and CD same in size. Same in size. There is no increase in length, there is no decrease in length when before bending. Before bending. So whenever the beam is subjected to a transverse load, definitely the beam is in bend. It is the new position of the beam. Say this is the plane CD, this is the plane AB, right? So this is the lower layer, this is the upper layer. So there is a layer represented by the NA, right? So we know the layer EF. We know the layer EF. So this is the layer EF. This is EF. Suppose if you observe all the layers, I think that so this layer is decrease in length, this layer is increase in length. It means there is a deformation. There is a deformation. So if you observe that before and after bending, if you observe the layers before and after, some of the layers decrease in length, some of the layers increase in length, but one of its layer neither decrease in length nor increase in length. That layer is called as considered as a neutral axis. Very simple one. So in a neutral surface, no doubt at all. So if you observe that whenever the body is subjected to a bending moment which results in a particular shape, just we have to measure the resistance offered by this body is subjected to a bending moment called as bending stress. So bending stress. So what about the stress induced in a particular layer that may be measured from the neutral axis? For that, simply let us consider the geometry. This is theta. For example, this is the R. This becomes Y. So from the geometry, finally we derived an expression M by I is equal. So sigma by Y is equal E by R. So one equation is derived from the geometry, that is the relation between M by I and sigma by Y and E by R. Here, where M is the moment and I is the moment of inertia, M is the bending moment, I is the moment of inertia about the neutral axis, Then sigma is the bending stress induced due to the bending moment caused by the transverse loads. So here particularly we consider a length of dx in a pure bending portion in the CD. Then E is the Young's modulus for a particular material, or is the radius of curvature. So by using this equation we can find out either M or stress Y if E and R given and Y is known, at which layer, at which distance you have to measure the bending moment. So the next one is to be calculation of moment. At which point the moment is, and then calculation of the stress. So what we have to calculate? We have to calculate bending moment M and bending stress. Before going to, let us see, so moment of inertia of various cross sections about this neutral axis. Before going to that, what about the stress distribution? So simply we can plot the graph. So what about the graph? Let us see the, what about the graph? This is a beam after bending, right? After bending, as we know that this is a layer neither increase in length, decrease in length, called as neutral axis, represented by A, and then the radius of curvature for this is, or simply it would be the theta, right? So what about that? Let us consider one more layer at a distance y below the neutral axis, right? This is y. So I think that if you observe the bending stress with respect to the neutral axis, right? What about the stress in a particular portion above the neutral axis? There is a compression. It means there is a decrease in length. Whatever the amount of the resistance offered by the body to the bending moment in such a way that graphically represented compression. So this is compression. Right? This is compression. So what about the stress? So you know that stress is resistance offered by the body to the deforming force, as we know that. Whether it is deforming in a particular shape or increase or decrease in length, or whatever the changes in length. And there is a stress in tensile in nature. Tensile in nature. So how can we draw the flat? Simply, whenever a bending moment is acting on a body or induced on a body, there is an increase in length. It means, or which results, tensile stresses are induced, which is below the neutral axis, and compressive stresses are induced due to the bending moment caused by the transverse load applied on the beam. So this is the compressive stress represented for our convenience, sigma c. So and tensile in nature, that is represented as C. So this is the way to represent the bending stress and bending stresses, compressive nature and tensile in nature, subject to a various types of the loads. Now the second one is the next one is the calculation of bending moment. So how we calculate the bending moment? So very simple. Let us consider a simply supported beam. Here calculation of bending moment. So let us consider a simply supported beam as shown in figure, subjected to a uniformly distributed load over entire span at the rate of loading or intensity of loading is W Newton per meter, for example. So what we have to do? Just I would like to find out the bending moment at a particular position C, a particular position C. For example, what about the reaction at the support A? What about the reaction at support B? We can calculate the reaction at support A and B simply total load divided by 2. If the length of the beam is, for example, L. What about the total load? W into L. RA definitely WL by 2. Again WL by 2. You know that. RA and RB. Just I would like to find out the bending moment at a particular point C. It means at a distance, for example, A. So what we have to do? Just we have to formulate the bending moment equation. So for that, just simply write down the bending moment at a particular section XX becomes RA into X. For example, it is at a distance X. And then what about the moment produced by the uniformly distributed load distributed over a distance A? Simply that is Wx. It is Xi. It is X. It produces the moment in opposite direction to the moment produced by the RA. So it would be Wx into X by 2. So this is the equation to know the bending moment at any point. So as we know that m by I is equal to sigma by y is equal to E by R. So we can find out the moment produced by any kind of the system of forces at any point with this way. Next, coming to the moment of inertia of various cross sections. Let us see what about the moment of inertia of a particular cross section, say as rectangle. One is the rectangular cross section. So suppose if you know the dimensions of the rectangular cross section, say as this is the rectangle of base B and depth D. Here we always find out the moment of inertia of a particular cross-sectional area about its central axis. Say this is the central axis, called as neutral axis otherwise. What about the moment of inertia of a rectangular cross-section of dimensions base B and depth D? Simply BD cube by 12. If it is hollow section. Say the same one is in a hollow section. The dimensions of the hollow section base B with depth D, right? So some portion is removed of dimensions, say as small b, and its depth is small d. Then we have to find out the moment of inertia of hollow section about its neutral axis or central axis. Simply becomes that would be BD cube by 12 minus small BD cube by 12. So before going to find out any one of its parameter, you must know the magnitude of the moment and magnitude of the moment of inertia of a particular cross section about its neutral axis. Similarly, we can find out the moment of inertia of now let us see. Next, moment of inertia of a circular section of diameter small d, for example. So we can find out the moment of inertia of this one about the axis which is drawn diametrically. So it is simply pi d power 4 by 64. In engineering mechanics, we know the moment of inertia, how the moment of inertia of a particular cross-sectional area about its particular axis is known. So then, coming to the hollow section, this is a diameter of the one circle in which there is let us see capital D. This is capital D. So what about this is capital D. It is the small d. So from that base formulation, so the moment of inertia of the shaded region, simply the moment of inertia of the shaded region is pi capital D power 4 by 64 minus small pi small d power 4 by 64. Finally, that is equal pi by 64 into d power 4 by minus d power 4 by capital D power 4 minus small d power 4. So, we know the moment of inertia of various cross-sectional areas. From the equation, m by I is equal stress by y is equal and E by R. So, then let us see the other parameter, calculation of stress. Calculation of stress, that is the bending stress. So first of all, if you know the m value, so don't bother about that. If it is not given, we have to calculate the bending moment by formulating the bending moment equation, just we discussed now. And if it is not given, I value is not given, you can find out the moment of inertia of a particular cross section about its neutral axis if it is not given. So then, y is a measure, y is the important value. It is a distance from the neutral axis to the particular layer. So it is to be important one. Then V is the Young's modulus and the radius of curvature is also given. Here we have to calculate the mi sigma if it is not given. If it is given, don't bother about that. So then last one is in the bending stress calculation part is the composite beams, composite or flitched beams. Composite or flitched beams. I think that this word is very familiar, which is discussed in the first unit itself. It means it is the combination of two or more different materials. Let us say this is one material. For our familiarity, it is wood. Simply it is wood, for example. Say wood. This wood is clamped with a steel plates. This is the one steel plate at left end. It is represented as shown in figure. This is the steel. So this is the. So these are the steel plates. Alright. This is the wood. So simply it is the combination of two different materials like wood and steel rigidly. So simply rigid with the both the ends. So here we have to remember only one point. So that is strain is same in both the material whenever it is subjected to a transverse load. For example, the strain in the steel is represented by epsilon s. So then the strain in the wood, it is one important parameter or condition while determining the stresses in the flitched beams, particularly combination of two or more materials. As we know that from the Hooke's law, so that is equal Young's modulus is equal, or that is from the Hooke's law, stress is directly proportional to strain. That is replaced by the constant proportionality. So that is equal to stress is equal E into strain. From this equation, E is equal to stress by strain. From that, finally, strain would be rewritten as Young's modulus stress by Young's modulus E. So from this concept, we can find out the here you can find out the bending stress if it is not given. If it is given, substitute. So this parameter or this information is very important one. So we have to calculate the stresses induced in a particular material. So that is stress induced in the steel as well as stress induced in the wood also. So finally, what we did today, simply we discussed or summarized so many parameters, particularly in calculation of the bending stress in the beams. So in the next class, we will summarize the shear stress induced in the beams. Shear stress induced in the beams. So, thank you.